All right. Well, I hope everyone's doing all right. My name is Freddie Drennan. I am a data optimization engineer. At least that's my title for a company called Digital First Media in Denver. And I've always been fascinated with certain type of optimization technique called linear programming. Integer programming would fall under linear programming. The only difference being that your solutions are all integers or binary variables. And it's really useful whenever you're trying to choose optimally or um, decide something optimally. Now, that doesn't really make a whole lot of sense right now, but I will just show you an example. Let me just open it up here real quick. This is an application that I wrote based on a problem that I just saw one day, and I thought it would be interesting to write out. So, say you're an airline company and you want to pick the best locations to put some airports. Now, you might have airports all over the United States, but you want like a couple hubs. And what I mean by that is um, airport locations which kind of service other smaller airport locations. And I am not sure what's going on here. I think I need to update my Shiny app stuff. It's not super happy with me. I think I'm hitting my limit on data. Um, Anyways, it should come up here in just a second. There we go. All right. So, say for example, you're like, I don't know, the U.S. government, and you want to pick optimally, some of these locations. So, for example, like here in Salt Lake City, we have a hub which services these four locations. You have another hub here which might service these other locations. Um, so the issue here is that um, you don't want to have to build more airports than is necessary. You don't want to have a major hub in every single location. You might say, well, we'll have a certain hub within a particular distance. And this would, obviously save money and you can cover the most ground as possible. So what happens if we say that, well, the hub, it can service not 750 miles, but instead it'll be able to service airports within, say 1,200 miles. Well, what you'll see is that if that is the case, if it can service more distance, then you might need less airports. And there's obviously a optimal solution where these airports, have travel the planes flying from these have to travel the smallest amount of distance to cover this entire region. What happens if we say, well, okay, but Salt Lake City is not actually an option? Well, if we remove Salt Lake City, well, let's put Salt Lake City back in here. I'm sorry, guys and gals. I think that what's going on is that there's kind of a big problem, and it's just kind of RAM intensive. Um, so here, let's do this. Let's decrease the minimum service distance. We'll say that we can service larger locations. Have it run. But then what if we remove some of these options? So let's see here. If Atlanta is no longer an option, which was down here, um, I should learn my my cities. Here, let's pull out Houston. Clearly, I didn't pass geography. So if we remove Houston as an option, then the hub moves over to the only location that I can service. So if the minimum service distance is like 1 mile, then obviously, and maybe not obviously, but hopefully it will be soon that every airport is going to have to service itself. So this is what you would call integer programming, but linear programming and integer programming, they're very similar. And so I'm just going to go ahead and get right into it. Um, first, the way that you would think about this, or any set of equations, is that the way that linear programming works is you have a particular function that you want to maximize. So for example, x1 plus x2. This is a completely valid function. You don't have to have an equals or whatever, because we're actually trying to find the max or minimum of a particular function. You know how some functions, say you had like negative x squared, the maximum of that function would be, 0 right here. The minimum would be negative infinity. And so we're looking for these points in these functions based on particular constraints. So if we were to say, well, just maximize x1 and x2, well, right now, what we're going to say is that, well, the maximum of this function is infinity, right? Because if you can put any number in here, and just blast it off into oblivion, and now it's infinity. But that's not very useful. Say, for example, you were trying to, I don't know, like sell corn and wheat, right? So this might be 2x1, so this is dollars per wheat, and then this would be like 3x2, so $3 per corn, where x1 is wheat, x2 is corn. Well, if this is, a profit function, well, if we wanted to make the maximum profit, then we would say, well, sell infinity corn and infinity wheat. Well, that's not really feasible in the real world. The real world has limitations, and that's where linear programming and integer programming come into play. So what would happen if I said, okay, well, we're going to maximize this function, and just to keep things simple, I think we're going to say x1 and x2 can only be integers. Actually, not only integers, but they can only be binary. And what this means is that x1 and x2 can only take on a 0 or a 1, right? Actually, let's not do that. I'm sorry. Let's take this back just a step here. We're not going to get into that quite yet. Let's just say we've got this here. So what happens if x1 and x2 can be any number? Well, what is the maximum of this function if we say x1 it has to be less than or equal to 0? Well, if x1 has to be less than or equal to 0, but there's nothing constraining x2, then the maximum is still infinity. This can be 0, but x2 can take on any value. But what if we said, okay, x1 has to be less than or equal to 0, but then x2 has to be less than or equal to 10? Well, in this case, the maximum of this function would be 10, because x2, the largest number that x2 can take, and so you just kind of plug that in there. What if we said get the maximum, but x1 can also be 10? Well, then the maximum of this function would be 20. Now, what if we said the opposite? What if we kept those same constraints, but then we said the minimum of this function? Well, the minimum is infinity, and these constraints aren't bounding this solution anywhere. So, you think of this x1, x2 as some sort of some sort of line in space. If x1 has to be less than 10, so this has to be less than 10, and then x2 has to be less than 10. Well, this entire region has plausible solutions, and the minimum would obviously be down here. However, the maximum, if we wanted to, and I'm just going to erase this and kind of clean it up in a second here. If we looked at this now, so x1 is, this is x1 equal to 10, and this is x2 equal to 10. If the only plausible solutions are in this field, but we want to maximize this function? Well, the maximum of this function up here, if we're kind of pushing this line as far as we can possibly go, you eventually get to a point where it just kind of lands right there. And think about this, right? So if this is 10, 1, 2, 3, 4, 5, 6, 7, and 10, and then this is 1, 2, 3, 4, 5, 6, 7, and 10. If we said 10 plus 10, well, this is the biggest possible number. This is, that would be 20 here. If we picked any other solution, you just say we stopped up here. Well, this would be x1 is equal to 0, but then x2 is equal to 10, which is not the maximum. So you kind of push this function all the way out until you find a corner. And that's kind of a graphical explanation of it. Now you can get more complicated. You could say 2x1 plus 3x2 has to be less than or equal to 200, or 5x2 plus 3x2, sorry, x1, this should be x1, is, has to equal 100, and then x1 has to be greater than or equal to 0, x2 has to be greater than or equal to 0. So in this way, and actually let's just leave this at, sorry. Yeah, we'll say this has to be less than or equal here. Without thinking about the number specifically, what would this look like? Well, we would have, first off, x1 has to be greater than 0. x2 has to be greater than 0. So we've already kind of ruined these possible solutions. And say this is some sort of economic model where you're dealing with profit. You're not going to sell like negative acres. Well, I mean, you might like sell them short or something, but we're not going to get to that right now. And then these other two lines are somewhere, like up here, there might be a line where it says, everything, beyond that, and then down here, there might be a line saying, everything has to be less than this. And so if you're looking at these different solutions, the only possible region that you could have solutions would be inside this little, God, I don't even know the math term, this little shape here. This would not be a solution because it doesn't include everything below this point, and this would not be a solution because it doesn't include everything below this point, right? So this is the feasible region here. And possible solutions would be this corner here, this corner here, this corner here. And typically, unless it's a straight line, if you got a little kink here, I think that this is almost always the best solution because you're kind of moving that line until you get to the end. All right, well, that's a big mess of stuff here. Let's go into the next problem. And we don't have to delete that. All right, so wheat and corn. And I promise that this will be the most boring problem that we do, but then that there will be more interesting ones here in the future. All right, so a farmer owns 450 acres of land. So we've got 450 acres. And he is going to plant each acre with wheat or corn. Okay, our decision variable is x1 is equal to acres of wheat, x2 is equal to acres of corn. And it says each acre planted with wheat yields $2,000. So this is a problem about maximizing profit. So our objective function is going to be what we want to maximize. So we're going to say we're going to max 2,000 x1 plus, and then the corn yields $3,000. So this is going to be $3,000 x2. So that's $3,000 per acre. Now we talked earlier, right? So we know that wheat costs $2,000 per acre or the profit is $2,000, and then for corn the profit is $3,000 per acre. However, we don't have infinite acres and we don't have infinite resources. And so all of these equations we're going to write within, thinking about x1s and x2s, or in units of acres. So all these variables need to have consistent units with themselves up here. So let's see here. Each acre planted with wheat yields $2,000 profit. It requires 3 workers and requires 2 tons of fertilizer. So we're going to be dealing with workers and fertilizer. And this is for wheat and corn. These variables are wheat, corn here, wheat acres. So how many acres does it take, or sorry, how many workers does it take to work on an acre of wheat? Well, it says it requires 3 workers. So you've got 3x1, 3 workers per acre. And given that this kind of column is going to be our workers, let's look at what it takes for corn. And each acre of corn yields 2,000 profit. It requires 2 workers. Okay, well, plus 2x2. And there are currently 1,000 workers, so we can only have up to 1,000 workers. Next, we'll look at fertilizer. The wheat requires 2 tons of fertilizer per acre, so this is going to be 2x1. And then the corn, for fertilizer is going to require 4 tons of fertilizer. So this is 4x2, so this is 4 tons per acre. And there are 1,200 tons of fertilizer available. And so that's what we've just formulated this equation here. So let's just write it out a little bit easier. So first off, we don't really have to think about these x1s and x2s at all. If you're familiar with linear algebra, you can just write out all the coefficients. And so there's kind of 4 pieces to writing an LP, or a linear program. First, you need your objective function, which we can simply write as 2,000. 2,000, just as a list of numbers here. And then the workers and fertilizer is another piece, so this is the objective function. And then we've got a constraint matrix. Which is this little piece here. So in our, like I said, there's 4 pieces. There's the objective function that you're going to have to input. You're going to have to put in a matrix of the coefficients here. So in R, that would be like a 3, 2, 2, 4. You're going to have a vector of directions. So you're going to have like well, I guess in R it would look like this. And then you're going to have a vector of the actual constraint variable. So that's 1,000, 12,000. All right, so let's look at this in R now. Just going to load some packages that I'm going to use for this. LP solve is the one that we're going to be dealing with. So the objective going in is this profit function where we have $2,000 for wheat and then $3,000 per acre of corn. This constraint, this constraint matrix is what we just talked about over here, where we're looking at this 3, 2, 2, 4. Just want to make sure that this comes back the same solution that I thought it should be. Well, what's going on here? I think that I ended up writing this a little bit backwards. Let's see here. Workers requires 3 workers. Three workers, 2 workers, 2 fertilizer, 4 fertilizer. Yeah, 10, 1,000, 1,200. Oh, okay. I just wrote them a little bit backwards here. I'm going to keep this consistent though with just the order of things. Just need to make sure because I know what the right solution should be, and I just want to make sure that we're okay. Yeah. So then I need to just reorder this, and then it should be fine. Sorry. Yeah. Okay. So we have this constraint matrix. What was it? The workers and fertilizer. This is workers. This is fertilizer here. And then we've got the vector showing the direction, which are going to be both less than or equal to. And then this is the constant right-hand side where, we know what this is going to look like. But this is the, it has to be less than 1,000 workers and less than 12,000 tons of, or 1,200 tons of fertilizer. And so once we've built out those 4 pieces, you just throw them in here. We're going to say we're going to get the maximum, and then you just, pop them all into this LP function and then get the solution. Well, what does that tell us? It says that the objective function is 1e plus 06, or 1 million, and that's the profit. So if we were to take this objective in, which is, how many dollars per acre, and how many dollars per acre for corn, wheat and corn, we can look at what these x variables are actually. So we're going to run, or we're going to, plant 200 acres of wheat and 200 acres of corn. And then if we do some matrix algebra, well, actually, we don't have to do that. We can just multiply the objective n times solution. And so we're going to get, this much profit for wheat, this much profit for corn, and then if we just sum it up, then we get 1 million. Oh, sorry. The same thing as multiplying and summing would be some matrix multiplication. So you can do objective n, and then do some matrix multiplication, solution, and then that still gives you the same answer. So what does this look like in a plot? Well, we have, this is our objective function, which as you increase the x1 and x2 values, it gets closer and closer and closer to this point here. The constraints are these equations going across where, you've got them, I don't even remember the specifics, but, you have these inequalities which say that this is a region which, you're able to have a solution in. And so these point solutions would be right here, and right here. And where you don't see these colors meshing, those are, places where there's no solution, because while this satisfies one inequality, it doesn't satisfy this inequality. So you're going to have an area where you have each colors, and obviously these graphical solutions aren't something that you can do everywhere. Obviously if you're like a 100-dimensional matrix or something ridiculous, it's just not really plausible to do such things. But anyways, this is my quick and dirty introduction to linear programming. I hope that it was useful. I hope I didn't ramble too much. The first thing that I showed you was an integer program. I will go over that at a later date. And there's also a integer program, which, like I said, it's just like a linear program. Only the way that you set it up is very similar, except that you're just saying that you have integer or binary variables only. The methods for solving those are a little bit different, but we can talk about that at another time. So hope this was useful. I will post this script for anyone who would want to see it, and I will put the link under this video. All right, well, I hope that you have a good day. Bye-bye.